All right, welcome to the introduction video of my Technical Art 3 project. So in this project, I focus mainly on making an explosion simulation, as well as making two tools for fracturing. So the first tool I made is a concrete fracturing tool. So the reason I made this tool is because the default um, material fracture and Boolean fracture are quite slow and inaccurate at sometimes. So I made my own tool, which first of all drastically increases the efficiency of the fracturing process, and secondly, it it also saves more time and is more accurate on the results. So in the fracturing tool, I made another tool called the recursive fracture. So basically, we have like different controls to it. The first one is the main control, which acts as the base fracturing. So here, let me just show the fracturing. So the model we're taking here is the building wall. All right. So here's our first layer of fracturing. So in this fracturing tool, we have the first recursive fracture. Let's quickly add a explosive view to it. All right, so that's the first layer of fracturing. And as you can see in the controls, we can do, you see 20 layers of fracturing. And then we can also control the fracturing noise frequency, which will change the results. I'm not going to change it here because I have my simulation already set up. So it's also we can also increase the noise frequency, which will change the frequency of the edge damage over here. And then next we have like the second layer. So each of those fracturing takes care of a layer. So based on the previous fracturing, with the second recursive fracture, we can do a second layer fracturing, and it splits it up into more pieces. Here is 5 pieces, and we can have like 2 variations. So we can either do 3 to 7 fractures. So it's like random. Also, we have this the same amplitude and noise frequency setup, and same as the second layer. Here's the third layer, where we split it up even more. So here I set it to 3. Okay, so the basic trick to it of increasing the efficiency is creating a compile block. So it is the same as creating a function for in Python or in C++. And then I avoided using the default fracturing tool. Instead, I used my own system where I cooperated with the Voronoi fracture over here. So in this way, so I did a remesh. I also like did a couple of things so that I can have more at the same effects, same results of the material fracture and have it as a more stable tool. So yeah, that's basically it. And then the thing that's pretty interesting here is that we can actually separate the 3 different layers using color. So with this color 4, we can show the level 1 fracturing. With the other color, we can show level 2 fracturing, and then level 3, we can show level 3 fracturing. So these things are pretty crucial for artists when they can art direct each individual layer and decide how they want to fracture the structure. So yeah, that's all about my concrete fracturing. So here I'm going to introduce you to my wood fracturing tool. So same place over here. Yeah, so there's this huge compiler block which increase the efficiency. So the idea is that we use a multi-thread compiler, which means that we use the other cores of our CPU and then do each individual loop, spread each individual loop into different cores so that it can work simultaneously and give me the result faster. So here I did first of all a slice tool. So this is the model I'm taking in, which is a simple window, and I'm going to fracture it with wood, with the pattern of wood. So here I first did a slice tool where I sliced them into more pieces. So model prep is pretty important in terms of fracturing because we have to prep the model and make it fracture ready, right? So over here, as you can see, I divided it into 4 pieces, and then for each individual piece, I did a bunch of like vector calculations, so that so first of all, I put all of those different fractures, different pieces, down to the origin. So as you can see, I put them down to the origin, and then over here, as you can see, here is a let me see if I can show you everything. Oh, so yeah, it's in a for each loop, so I can only show you each individual piece. So as you can see, the piece is locked down to the origin, and then each piece every piece is locked down to the origin, and then we can do a Voronoi fracture. So first of all, we shrink it down 10 times, and then we spread points on the shrink down version of it, and finally we put it into a Voronoi fracture and then stretch it up. So that's how I got the wood kind of like pattern, as you can see here. Right, so that's how I get the wood pattern out of it, and then I did a inverse matrix and then put it back to where it was previously. So I put them all back to where they were previously, and then I did a RBD cluster, which I clustered the broken pieces into larger pieces so that they resemble a real fracturing wood in the real world. So yeah, I did it for each individual window, and then I plugged it back to my procedurally generated house to fit them in their places. So the next step of the fracturing is making constraints. So I did a huge constraint network based on the models I have. Yeah, I wonder why it's still staying on. Oh, it's okay. Constraints. So I made a huge constraint network of the house. So right now there's only the windows and the concrete walls, but in the future I'm going to add more metal and other materials, right? So yeah, after the constraint network, I made a force. So the force activates on, I think, on number 6 frame. You see, it's just a huge point cloud that has, I think, yeah, the force, the force generated, and I can move the force origin. So you see, there's a point over here. If I move it, it's going to move the force to a different direction, and I can control its amplitude by scaling the vectors up. So with the force, constraints, and the fracturing, I finally go to the RBD sim, where I simulate the entire destruction in the DOPNet. So this part is pretty simple. We just hook stuff up, and boom, here's our final result.